remember what we're talking about. We are talking about, what are we talking about?
Limits and sequences.
Limits of sequences, and what is the idea? What's a limit?
It's like a number that a sequence approaches.
A number that a sequence approaches.
As
Okay.
n.
If there's every epsilon that's greater than 0,
Yeah.
there exists an n that's part of the natural numbers classification.
Limits of sequences. Yeah, so it's right. There's sort of the intuitive idea, right? There's this number that you get closer, you get arbitrarily close to as time goes towards infinity, right? I tend to think of this of the natural numbers as time, right? There's a ticking clock here, 1 time 1 time 2 time 3. As time heads up towards infinity, right? Your sequence tends towards a certain limit, right? Tends towards a certain number, right? But then there's the formal definition, right? That given any epsilon greater than 0. So let me say it this way. We say that the limit of a sequence is L if given any epsilon greater than 0, there exists a time such that past that time, then a sub n, the distance from a sub n to L is less than epsilon. Right, so this is the formal definition. Right. In other words, in English, given any tolerance, that's your epsilon, there is a time past which that tolerance is satisfied. In other words, the distance from AN to L is less than that tolerance. So, right, this is sort of like the, you have I tend to think of this sort of thing as you have a initial vague intuitive idea, you have the mathematical definition of that vague intuitive idea. And then you have sort of an intuition about that, you have an intuitive idea about that mathematical definition. Okay. So this is saying that given, if somebody wants you to be, this close, if somebody wants you to be this close to L, there's a time past which that happens, right? And for the limit to exist means that no matter how close you're required, there's a corresponding time. There's always a corresponding time. Whatever epsilon you're given, there's a corresponding time past which that epsilon is satisfied. Okay. So we can use this to prove certain facts that you think should be true. So there's a theorem about the uniqueness of limits. That is, there's nothing in this statement that says that L has to be unique. Okay. How do you know that there couldn't be another L that works? Okay. But built into this definition are constraints that force L to be unique. Okay. So it's this, right? If L and M are both limits of the same sequence, then L must be equal to M. Right? There's no way you could have two different limits. And so you can do this in two different ways. So you can use this formal definition to prove it in two different ways. I think the easiest way is probably to do it by contradiction. Okay, so at this point we go to our intuition about the definition. Okay, you say, well, look, let's think about it, right? If you have two limits, you suppose you have two numbers and they're different, and they're both the limit, right? There are two separate numbers over there, here, wherever, and they both have this property that we can make the sequence as close to each as we want, right? Why does that lead to a contradiction?
Because if it's close to one, it's not going to be close to the other.
Right. So how would you make that contradiction evident? Well, you'd say, well, I'm going to make everybody super close to this guy, and that'll force them to be away from that other guy, right? Well, how close is super close? I don't want to choose my epsilon to be huge, right? What should I choose as my epsilon for this idea of super close? Close enough. How close do I want to require my elements to be to this upper limit guy? Let's call this guy L, this guy M. Say. Right. Well, the distance between them...
Some distance between the sequence and the limit?
Well, so the sequence is, remember, sort of going all over the place. It tends towards these two things. Right? So here's L, and here's L, and here's M. Say. Right. And we are saying that the sequence tends to both of them, right? We're saying that the sequence tends to both of them, right? That means that given any tolerance, I can make my sequence within that tolerance, right? So given an epsilon, I can find a time past which everybody is within that epsilon of L. Okay, right? Given, right, I can find a time past which all these guys are within epsilon of L. I don't know, maybe some time over here. Okay, right? Okay, but how should I choose my epsilon? What I want to say is that, well, if I make these guys close to L, I can't have them also close to M at the same time. Right? So how close should I make them to L? Aria?
Epsilon would have to be less than half the distance between L and M.
That'd be great. So let's choose like epsilon to be like this. Okay, so that will work. Choose epsilon to be the distance between L and M divided by 2. Okay. So here's my L, here's my M, and I choose my epsilon like this. So this is L minus epsilon, this is also M plus epsilon, and minus epsilon, plus epsilon. Right. Okay, and so I know that there's a time, n1, since L is a limit, there exists a time n1 past which the distance between an and L is less than epsilon. Right? But then, so I know that everybody past this number lies between these two bars, right? Lies between these two parentheses, right? But I also know that M is a limit, right? So I know there's another time, N2, past which all elements lie between these two bars, right? And you see how the contradiction is taking form, right? There's, similarly, since M is a limit, there exists an N2 past which the distance between a sub n and m is less than epsilon. Right? And you see that that's going to be trouble, right? Because we're saying that everybody's between these two bars, and everybody's between these two bars also, right? And so there's a contradiction because these two things don't intersect each other, right? These two ranges don't intersect each other, right? So you say, well, look, that's for n past the greater of those two, we have that the distance from a sub n to L is less than epsilon, and the distance from a sub n to m is also less than epsilon. Right? But that's problematic. So what we're saying is that that everybody past the bigger guy. So in this picture, this is the bigger guy. Right? This is the max of n1 and n2. Right? Everybody past this point lies in both intervals, right? Which is impossible, right? Because these intervals don't intersect each other. Right? Okay. So let me. Let me show you one way of making that clear. You'd say, but then the distance from L to M which we can rewrite as L minus a sub n plus a sub n minus m. So I'm going to do something using the triangle inequality. This is kind of a trick. Okay.
Sorry, how did you get from L minus m to L minus a sub n? Oh,
because I added I added 0. Okay. So often you add some clever looking 0. Okay. This thing is less than or equal to, by the triangle inequality, less than or equal to this. But each of these guys, remember this guy is less than epsilon and this guy is less than epsilon, right? So we get, this is strictly less than 2 epsilon. Yeah.
Can we say, so we have L minus a sub n in absolute values, but then we previously had a n minus L?
Yeah, but those are the same thing, right? Because the absolute value of A and negative A are the same. Right, if I take the absolute value of A sub n minus L, that's the same thing as the absolute value of L minus A sub n, because it's just multiplied by negative 1. Right, so the absolute value of negative something is just negative 1, the absolute value of negative 1 times A, which is just absolute value of A.
Thank you.
So yeah, so it doesn't matter. It doesn't matter. Okay, and then you'd say, okay, this 2 epsilon is the absolute value of L minus m, right? Because our epsilon was L minus m over 2. Okay, and so what you would end up with is that the distance from L to m is strictly less than the distance from L to m. And that's a contradiction, right? Which is a contradiction. Because you end up with this guy being strictly less than itself, which is impossible. So the intuition is well, look, these two intervals don't intersect each other, and so it's impossible to have a point that lies in both of them simultaneously, right? But to prove that, you have to do something like this, basically. To prove that these intervals don't intersect each other, you say, well, suppose there's a point that lies in both of them. Well, then you'd end up with this crazy contradiction. Okay. So this is a typical sort of limit argument. Okay. You say, well, look, if each of these guys is a limit, then we can make them close to this guy and close to this guy. There's a time past which they're close to this guy. There's a time past which they're close to this guy. Well, that means if you take the greater of those two times, then past that, the larger of those two times, then you lie in both of them. Okay. So this sort of taking multiple times and then taking the greatest of them and sort of getting all conditions to apply at the same time is pretty typical. Okay, any questions about it? Any questions about it? What are we missing? Wait, Mark. Okay, so now, this is what people would call, I think people call this soft analysis. Now we're going to do stuff that's more like what people call hard analysis. And it has nothing to do with difficulty. It's just the style of argument. Okay, so what we're going to do now is section 8. Epsilon delta style arguments. Actually, I shouldn't say epsilon delta, epsilon n style arguments.
When you said that we've been doing soft analysis, was that like everything?
Just this thing right here, just this last proof.
Mm-hmm.
That's soft. Okay. So we're gonna do a bunch of proofs of limits. Okay, we're going to prove that. How do you prove, right? How to prove the limit of something, the limit of some sequence is some limit, is some number. Right? We've got this definition. How do you use it? Okay, so we're going to start off with the simplest example. Right? Suppose that our sequence, A sub n, is constant. Okay. So this triple bar means is constantly equal to. Okay, right? In other words, an equals c for all n. Okay, and then we want to prove that the limit of A sub n actually is c as n goes to infinity. Okay, so you think of what you have to show, right? What do you have to show? What do you have to show? You need to show that given any tolerance, there's a time past which that tolerance is satisfied. Fine, right? So given any epsilon, there's a time past which A sub n minus c is less than epsilon. That's what you need to show. Okay. Well, you think about, so you consider this condition, a absolute value of a n plus c. Right? Being less than epsilon. But a sub n is always equal to c, right? In our case, a sub n is c. So we say, well, that's the same thing as the condition so the condition is this, right? And it's equivalent to requiring that 0 be less than epsilon. Right? Right? But 0 is always less than epsilon because our epsilons are positive numbers. Right? So what's the time past which the condition is satisfied? Well, any time, right? Any time will work, right? So what n works? What n is such that n greater than n ensures this, right? Any n. Any n will do. But if I turn it on or not. Okay, any n will do. Okay. Okay, so you do some scratch work. Right, and then you realize, after a few seconds that there's nothing to this. Any n will do, and so you write up the proof. So here's how you write up the proof. You say, right, we need to show that given any epsilon, there exists an n past which a sub n. Maybe I'll write that off just to be really clear. We need to show that for all epsilon greater than 0, there exists an n past which a sub n minus c is less than epsilon. Well, take n to be 1. For n bigger than that, we have a sub n minus c equals c minus c. C minus c, which is 0, which is certainly less than epsilon. Right. So that n works for any epsilon. Okay. Okay, so that's the simplest example, right? Not particularly exciting. Let's now do a simple example. Along the same lines. You say, okay, well, let's show that the limit of 1 plus 1 over n as n goes to infinity is 1. Okay, so our a sub n, this is our a sub n. A sub n is 1 plus 1 over n. Okay, so again, we want to show that for all epsilon greater than 0, there exists an n such that if you're past that n, we have that a sub n minus 1 is less than epsilon. Okay, so again, you do some scratch work to figure out what n has that property, has the above property. Okay, so you say, okay, let's look at the tolerance condition. Well, it's that a sub n minus 1 is less than epsilon. In other words, a sub n minus 1 is less than epsilon, which is the same thing as saying that 1 plus 1 over n minus 1 is less than epsilon. Okay? Because a sub n is 1 plus 1 over n. Okay, that's the same thing as saying that, right, the 1 and negative 1 cancel, right? And so we see that this is the same thing as saying that 1 over n is less than epsilon. Right? But that's the same thing as saying that 1 over n without the epsilon is less than epsilon. Right? Because n is a natural number, So the absolute value of it is is the same as the original. It's positive, right? Okay, but that's the same thing as saying that 1 over epsilon is less than n. That little n is bigger than 1 over epsilon. And so what we see is that, if little n exceeds 1 over epsilon, then in fact we get 1 over a sub n minus 1 is less than epsilon, right? Because we in fact have more than just an implication, we have an equivalence, right? That this condition is in fact equivalent to that, right? We don't need that. We only need the implication part, right? We only need the implication part, right? So as long as little n is bigger than this number, 1 over epsilon, then this thing is going to be within our tolerance. Then our tolerance condition is satisfied, right? So as long as little n exceeds 1 over epsilon, our epsilon tolerance is satisfied. Right? So just choose any capital N bigger than or equal to 1 over epsilon. Right? Okay. So that's your scratch work. Right? Figuring out the time past which the condition is satisfied. Well, we've done it, right? As long as we choose any big N that's bigger than this, we'll be okay. So now let's write it up. So when I was in college, one professor said to me, all math is done backwards of the way it's written. Okay, like when you write it up, you sort of write it up in the reverse order in which you discovered it. You say, okay, proof. Given epsilon, let n be any number such that it's bigger than or equal to 1 over epsilon. It's like pull that number out of nowhere. Like, that's it. Okay. If little n exceeds capital N, so then if little n exceeds capital N, which is bigger than 1 over epsilon, we see that the distance between a sub n and 1 which equals 1 plus 1 over n minus 1, which is the same thing as 1 over n, which is the same thing as 1 over n without the absolute values. This is going to be strictly less than epsilon, right? Since little n exceeds 1 over epsilon. So the limit of a sub n is 1. Okay, any questions about this? Yeah, Ari.
Sorry,
No,
so
no.
I'm with you until we say I'm good with since n is greater than 1 over epsilon, and the whole deal of epsilon is less than 1 over n. But then, how do we say that the limit is 1?
Because to show that the limit's 1, we have to show that given a tolerance, there's a time past which we satisfy the tolerance. Okay. And what we've done is shown that given any tolerance, we found an n so that if we're past that time, the distance between a sub n and 1 is less than epsilon. Okay, so we've done what we needed to do to show that the limit is 1.
So we were showing that there exists such a big N,
Yeah.
and, okay.
So, right, so maybe I should have again said, we need to show that given any epsilon, there exists an n such that if n exceeds that big N, then the distance from a sub n to 1 is less than epsilon. Okay. So maybe that makes it clearer. Right. What our goal is to do this, right? To prove the limit, we need to prove this that this is true. So, right. So let's say like this: fix an epsilon, and then let n be any number bigger than 1 over epsilon, and we see that n works. So we found the n that works for epsilon, right? And epsilon was arbitrary. So the limit is 1. Anyway, do you have a question?
And something.
Okay. So epsilon was arbitrary, so the limit is 1. Okay. Okay. We're going to do. Should we move on to the trickier guy? Let's see if we can get it. So here's another example. So a sub n is 2n plus 1 over 3n plus 2. Okay. And you probably expect, rightfully, that the limit is going to be 2/3. Okay. But let's prove that. How would you prove that? So, right. So let's show that the limit actually is 2/3. And again, we'll do it by doing a bit of scratch work. But the scratch work is going to be a little bit more complicated because of things, the way our code looks. Okay, so you say, again, let's look at the condition. The tolerance condition is this, right? That the distance from a sub n and 2/3 should be less than epsilon, right? So our epsilon condition, is this. And so you simplify it. Say, okay, well, let's do a little bit of simplification. You use some fractions, and you say, okay, well, this is the same thing as saying that 1 over 3 times 3n plus 2 is less than epsilon. So you do some elementary school fractions, you get this. But again, that's the same thing as saying that 1 over 3n plus 2 is less than epsilon. So we want to change this into a condition about n being bigger than something, right? Is this equivalent to little n being bigger than something? If it is, that's great, right? If we can get it so that this is the same thing as saying n is bigger than that something, we let our big N to be that. Okay, so there's 2 ways we can do it. So path 1 is to say, well, look, this is the same thing as saying that 1 over 9n plus 6 is less than epsilon. That's the same thing as saying that 1 over epsilon is less than 9n plus 6. That's the same thing as saying that 1 over epsilon minus 6 is less than 9n. In other words, n must exceed 1 over 9 epsilon minus 2/3. Okay. As long as n is bigger than that, then we're good. Okay, so this we could take as our n. In fact, this is the best n, right? I should say our lower bound for n, right? As long as n is bigger than this, as long as our capital N is bigger than this, then we're good. Okay, we just write up things in exactly the same way. But let me show you sort of a simpler way, a simpler but less precise way to have 2. You say, well, look, 1 over 3n plus 2, that's 1 over 9n plus 6. That's strictly less than 1 over 9n. Right? That's strictly less than 1 over 9n, right? Because here I'm dividing by 9n plus 6. Here I'm dividing by 9n, right? 9n plus 6 is bigger than 9n. Right? So I'm dividing by something smaller, I get something bigger. Okay. So you say, well, look, as long as 1 over 9n is less than epsilon, that's enough. Right? Because if this is less than epsilon, then this is less than epsilon. Right? Right? But then 1 over 3n plus 2 will be less than this 1 over 9n, which is less than epsilon. Okay, so the thing that we wanted to be less than epsilon, the thing that we needed to be less than epsilon will still be less than epsilon. So we choose something a little bit bigger and simpler to work with. Okay, we choose an intermediate bound that's easier to work with, right? So, and you see that this thing is easier, right? You say, well, this is the same thing as that n must be bigger than 1 over 9 epsilon. N must be, as long as, i.e., as long as n exceeds 1 over 9 epsilon, we're good. So take this, we could take this instead, right? As our lower bound for n. Okay. Okay. So, and again, you write things up in the same way. Right? You'd say, so the write-up would be choose n bigger than 1 over 9 epsilon, then if n is bigger than n, 2n plus 1 over 3n minus 2 minus 2/3 is the same thing as 1 over 3n plus 2, which is smaller than 1 over 9n, which is smaller than epsilon. Right? So this is how you would, this is the formal argument, right? Somebody gives you an epsilon, and you choose any epsilon bigger than 1 over 9. I'm sorry, choose any capital N bigger than 1 over 9 epsilon, and you see that as long as you're bigger than that, your tolerance is satisfied. Okay.
So on the homework, would you want us to see the scratch word and the formal proof?
No, actually, just the formal proof
Okay.
is enough. Yeah, yeah. But don't just put the scratch work. Do the formal proof.